Good morning or afternoon, everybody. It's great to see you, and we're going to be taking a look at work today and how work is related to energy. So let's get started. Get out your notebooks and let's write these notes down. Here's our essential question for today. How are work and energy related? So as we go through these notes, we're going to be investigating this. If you remember the work we did last week, you should be able to answer this question. But if you don't, hang on, we're going to get through this. Okay, let's move on. All right, we take a look at work here. Work, by definition, is the transfer of energy that occurs when a force makes an object move over a certain distance. That's our definition of work. And in order for work to be done, something has to move, and the motion of whatever it is must be in the same direction as the force that's acting on it. Otherwise, there is no work being done. Okay? And when work is done, a transfer of energy always occurs. Okay, down here in this little picture here, we got this person. He's sitting in a wagon. He's got a rope attached to a tree. And here's the situation. When he pulls on the tree, does the tree pull back? And does the tree do any work? Well, what do you think? I want you guys to go ahead and just talk about this with your neighbors and give Mrs. Parson an answer in just a second. Okay, now for the next question. If he stands still, does he do any work? What do you think? Go ahead and talk about it with your table and then give Mrs. Parson the answer. Okay, next here, we are going to be looking at how to calculate work. Yes, unfortunately, this is some math, but this equation isn't too difficult. It's really similar to what we've used in the past with only 3 variables in the equation. So here we go. Work is measured in joules, and it's equal to force, which is measured in newtons, times distance, which is measured in meters. So our formula for work right here, work equals force times distance. And here's an example problem we're going to work through together. You push a wheelbarrow with a force of 100 newtons. You moved the wheelbarrow 5 meters. How much work did you do? Well, we're going to approach this problem like we have in the past in all of the other problems we've done. We're going to take a look at what was the given information in the problem and how are we going to use that information in the equation above. So if we read the problem again, you push a wheelbarrow with a force of 100 newtons. We see here that we have a force of 100 newtons. So we have given F equals 100 newtons. All right, then we move on. You move the wheelbarrow 5 meters. 5 meters measures distance, so we have down here distance, D, equals 5 meters. Our question wants us to find out how much work did you do? So work here, W, is equal to our question mark. That's what we're trying to find here. Okay, so looking at our formula, work W equals force F times distance D. Straight up, we don't have to manipulate the equation or change it around using our formula triangle. We're just going to plug the numbers in, plug and chug, and do the math. So we've got work is equal to 100 newtons of force times 5 meters in distance. So that's pretty easy math. We can do that in our heads. If we have 100 times 5, the amount of work being done on the wheelbarrow is 500 joules. Okay, makes sense? Okay, next topic. Okay, next topic is it's related to work. It's called power. Power is the rate at which work is done. So kind of like what we looked at before with speed. Speed is the rate of the distance over time, and velocity was the rate of displacement over time. Okay, and acceleration, if you remember, was the rate of the change in velocity over time. So today we've got the rate at which work is being done. So when we calculate power, power is measured in watts, and it's equal to work measured in joules divided by time measured in seconds. So power equals work divided by time. All right? And the unit for power, there's this little cartoon here. What's the unit for power? What's the unit for power? And the answer is yes. So we measure power in watts. So like when you're at the store, you have to buy some light bulbs or something like that. A lot of times the light bulbs are classified in how much wattage is required for them to work. So how much power they use, okay, or how much electrical power they use. All right, here's our example problem for power. Let's say you do 900 joules of work pushing a fridge, and it took 5 seconds. What was your power that you exerted? As we read the problem again, we're going to look at our given information. You do 900 joules of work. So we've got work, W, equals 900 joules, and it took 5 seconds. And our time, T, equals 5 seconds. So our question mark here, which I forgot to write down, P, power, is equal to our question mark. That's what we're trying to find because that's what the question asks us to get. Okay, so we're going to use this formula in which we've got P is equal to W work divided by T time, and we're going to substitute those values into the formula. So power, P, equals 900 joules, we plug that in right there, 900 joules divided by 5 seconds. That's the time. So if you put that in a calculator, you would see 900 divided by 5 is equal to 180 joules per second. And joules per second is a derived unit in the SI system, which has a name. It's named after Watts, James Watts. So we say that it is 180 watts. So anytime you see joules per second, you can think watts, named after James Watts. Okay, guys, that's it for our notes today. This was pretty short and sweet. We are going to go ahead and make a little triangle defining work, and we're going to do some calculations next. So go ahead, get your notebook ready to add some more stuff to it, get your calculator out, and be ready to do some calculations. All right, see y'all next time.